Good morning guys, welcome back to my channel, and in this video we will be talking about preparation of haloalkanes using alkenes. Now the best method to prepare haloalkanes using alkenes is by the halogenation of alkenes. You're going to halogenate your alkenes, and this is fairly an easy video. It is an easy method that you will be studying here. Now let's consider an example. Let's say I have my alkene CH2 double bond CH2. This is my ethene, and I am going to react it with hydrogen halide. Now X could be anything from your halogen atoms, and the product that I will get is CH3 single bond CH2X. This is my haloalkane. This was the product that I wanted, and I got it basically from alkene. I reacted my alkene with hydrogen halide and I got my haloalkane. This is the basic reaction that you have to keep in mind before starting this video, that we are going to react alkenes with hydrogen halide. Now this reaction, if you know something about this reaction is electrophilic. It is an electrophilic addition. It is an electrophilic addition reaction. This is an important point right here. Now what is electrophilic addition reaction? You have studied these sort of reactions before also, but let's get a quick recap. So from electrophile, you can see electro is electron and philic is loving. Electrophiles are the electron loving species, and in this reaction we are going to add an electrophile. There will be an addition of electrophile that you will see how there is an electrophilic addition. Now first of all, let's consider this hydrogen halide here. From this, if hydrogen halide bond breaks, hydrogen will get a positive charge, exactly, and halogen will get a negative charge. Since hydrogen gets a positive charge, it is having a demand of electrons. Since it just lots its electrons from hydrogen halide, like halogen atom from hydrogen halide, so this is having a demand of electrons. It wants electrons, and that is why it is going to act as an electrophile. Now where does this electrophile gets its electron from? Yes, it gets it from your alkene, where there is a presence of loosely bonded pi electrons. There are loosely bonded pi electrons present, and your electrophile will get those pi electrons and will add to this alkene. So this is also called as an electrophilic addition reaction, where your electrophile is being added to alkene. Now moving on, if you talk about this reaction, if you notice something about this reaction or you observe this reaction, this particular reaction, my friends, is completely based on Markovnikov rule. Now I have talked about Markovnikov rule in my previous videos as well. I will give the link in the description, but let's get a recap of Markovnikov rule. Markovnikov rule says that if to an unsymmetrical alkene I am adding an identity with a polarity difference, then the negative part of that identity will get attached to the double bonded carbon atom having less number of hydrogen atoms. Let's see how that happens. First of all, I'm taking an unsymmetrical alkene here. I'm taking propene, which is unsymmetrical alkene, so it looks something like this: CH3 single bond CH2 and CH double bond CH2. This is my propene, and what I'm going to do with this propene is that I am going to react it with a hydrogen halide, and this hydrogen halide, let's say I'm going to react it with hydrogen chloride. I'm going to react it with hydrogen chloride. You can react it with any hydrogen halide you like, but I'm going to react it with hydrogen chloride. Okay, so first of all, your hydrogen chloride bond breaks, wherein your hydrogen gets a positive charge and your chlorine will get a negative charge. Hydrogen gets a positive charge, so it is going to act as an electrophile. So your hydrogen first of all comes and attacks your alkene. Your bonds will break and there will be a movement of pi electrons, and based upon the movement of pi electrons, there are two possibilities. There will be two possibilities in the formation of your product. Guys, this is simple, just pay attention on Markovnikov rule. If you know Markovnikov rule, then this will be fairly easy. So our first product will be your secondary carbocation. Let's say your secondary carbocation looks something like this. This is your secondary carbocation, CS3 CS single bond CS3. You can see that this carbon is attached to two carbon atoms, so that is why it is your secondary carbocation. And I'm also having my primary carbocation. This is your primary carbocation. Now when you talk about these primary and secondary carbocations, these are formed based upon the movement of pi electrons or the shifting of pi electrons from your reactant, that is propane. If your pi electrons shift over there, for example, so you'll have a secondary carbocation, or you can also have a primary carbocation, which is this particular carbocation here. This is attached to one carbon atom, that is why we call it as primary carbocation. Now I have already told you like a billion times that secondary carbocation is more stable than primary carbocation, and tertiary is the most stable of all the carbocations. So when you notice this these products, if you look at these products, you can see that this is your secondary carbocation, so it will form a major product because it is more stable, so it will form major. And this is your primary carbocation, so it will form a minor product. Having said that, first of all, look at these carbocations. You can see that you can talk about these carbocations. If you look at them, those are attached to two carbon atoms, and that is attached to one. That is why we call it as secondary and primary. Major product always will move forward in the reaction. Minor product does not move forward. Major product has a tendency to move forward in the reaction. Now let me clear this off and show it to you. Now you have your major product, CH3 single bond CH. This is my carbocation, and I am also having a CH2 CH3. This is my this is my secondary carbocation, and I am going to, now since this has a demand of electrons, it has a positive charge. I also had an electrophile, which is chlorine. This chlorine will attack to this particular secondary carbocation, and it will form a bond as positive negative attract each other, and my product will be none other than beautiful haloalkane. This is my haloalkane. This is what I wanted, and I've got my haloalkane. Now this right here proves Markovnikov rule. You can see that the carbon atom to which chlorine is attached has proved the Markovnikov rule. This reaction has proved Markovnikov rule. If you look at this particular carbon atom, this was the carbon atom, double bonded carbon atom, which was having less number of hydrogen atoms, and you saw that chlorine was attached to this particular carbon atom only. So this proves our Markovnikov rule. This was about the halogenation of alkenes, and it is an important part, but it is fairly easy as compared to other reaction. Thanks for watching, and I'll see you in the next class, and until then, take it easy. Please subscribe and like this video. Bye.